inviting me and giving me like this chance to share with you what I'm doing, and hopefully it can somehow help you to continue doing what you may be interested in. So in this case, I will talk today about information length. So I will try to define information length and its application to control and maybe modeling or analysis of dynamical systems. How which is the way I view this. And before just starting, I have to say that I have to give just a brief context about me, I think. And I am a mechatronics engineer, so I did my bachelor's in engineering, then I did a master's degree in applied math. Specifically, I worked with dynamical systems, control theory, and at the time I worked with fractional calculus, which is another field very different to this. And from that, I met, after my master's degree, I had the opportunity to contact Imaging team and start doing what I'm doing now, which is more related to physics. So it has been a long journey, actually, and it has been also a quite as well complicated for me in some sense. So today I will first try to describe what inspires this work, and then I will, as I said before, talk about information length. Then I will talk about automatic control and information theory, how I try to connect them, and also we discuss the future work and give some conclusions that I hope will be helpful for all of you. So what exactly inspires this work? Well, I actually love to understand about system dynamics in general. So how systems in phenomena of any kind work. And when talking about systems, there are systems who are called complex because they appear to have some sort of emergence or self-organization, things like that. And there is a lot of areas that discuss these complex systems. So as I told you before, I started in the master's degree by analyzing dynamical systems with the aim to control them, to figure out ways to manage to modify its behavior artificially. So that's something that I always have in my mind when studying something related to physics or mathematics. So in regards to complex systems, there is a field called statistical mechanics, which has been quite helpful when studying and analyzing and giving results about how or why these complex systems behave the way they do. And there is a recent trend in trying to understand the statistical mechanics by using stochastic processes or stochastic calculus. But this idea only works for certain kinds of complex processes. So we know that the classic thermodynamics, for example, which is also part of the statistical mechanics as well, in this area, this trend, studies macroscopic systems, but when they are in equilibrium, in thermodynamic equilibrium. So when we are out of equilibrium, which means we try to see things changing and in terms of the steady state, the probability distribution, we can rely on the stochastic dynamics and stochastic calculus. But these systems are, some of the systems that this describes are mesoscopic, which can be colloidal systems, molecular motors, or a pretty simple example, Brownian motion. So Brownian motion, for example, you can analyze some sort of thermodynamic quantities about it by using the stochastic calculus, which is something that I will discuss today. But this will have the idea that the system, whatever system you are analyzing, it's in a heat bath that is in thermodynamic equilibrium. Sorry. Okay. And well, this is a pretty nice example of one of these processes, which is some particles trapped by some optical tweezers, which can allow me to move them when they are suspended on a fluid. Yeah, and the idea is that you apply some coarse graining techniques to figure out a way to model them. And specifically, the stochastic dynamics are useful in this kind of systems because they do the following. They usually represent these sort of systems by using Langevin equations or stochastic differential equations, which have a stochastic term related to the fluctuations around in this case, the particle that is suspended over the fluid. So this stochastic noise, its width can change because of the temperature, maybe, of the fluid, and then it perturbs the dynamics of the particles. So this is like the some sort of toy model of in my opinion, of what is happening, right? But once, if you want to understand this and study how to solve this stochastic differential equation, maybe let's just give a brief example. You have to do a stochastic simulation. So let's take this second order system, very simple. And this second order system is just a mathematical model of this Brownian particle, which is suspended on a fluid, where we consider that the fluid is just a bunch of particles smaller than the particle that is suspended on them, and its dynamics, in that way we can describe its dynamics like using equation 2, where C is just a perturbation of the purple particles over the gray color particle here. And what you do is you solve the stochastic equations. You do some stochastic simulation. You solve the stochastic equation by taking an initial condition from a given initial distribution, and you compute thousands or if possible, 1 million of simulations. And from there, you can figure out what's happening, getting some statistics. And this is a way to study these systems. But from this analysis, you can also check another point of view by analyzing the Fokker-Planck equation related to that Langevin equation. And this Fokker-Planck equation is the equation of motion of the probability distribution over time. So it gives, as it says here, the evolution of that probability distribution, and it's also in terms of the parameters of the system. So you can also analyze that by solving this partial differential equation. And of course, it will be easier or more complicated depending on specifically the term of the potential. So usually the way to describe this Fokker-Planck equation is also like in equation 4, where we write this derivative of the partial derivative of the probability distribution over time as sum of a term we call the current. And that current, well, is described by equation 5. Okay. And if you solve that partial differential equation, this is what you may get, something like this. So as we can see, this is the case when we have some a potential which is harmonic, and this is a diffusion process, basically. And these are the parameters the space parameters, and also I am taking into consideration that there is a noise width. Okay. All right. So what's next? So thanks to this description, these mathematical descriptions, you can figure out all of things about these systems. And as we said, there was a trend called stochastic thermodynamics, as I mentioned in the beginning. So it means that maybe I can compute the thermodynamic quantities at every instant of time by knowing the probability distribution at every instant of time. So a way to do that will be to figure it out first, maybe to try to compute entropy, for example. In statistical mechanics, entropy is a measure of the number of ways a system can be arranged, and it's often taken to be a measure of disorder. The higher the entropy, the higher the disorder in the system. This is what is commonly described as entropy from the field of statistical mechanics. But when you have these stochastic differential equations that describe the motion of a random variable, you have to use something called differential entropy. And differential entropy in this case is the entropy of a random variable. And this is viewed as a measure of the uncertainty of an event. And the maximum entropy is achieved when by a distribution that exhibits the highest probable randomness. So as you can see, this definition allows me to understand how the uncertainty of the events appear, and also it's applied, it can be applied, as we can see, to these descriptions given by the Fokker-Planck equation or by the Langevin equations. So we can also think about computing entropy rate, which is the time derivative of entropy. So we can see the trend of change on entropy in the stochastic processes. And well, that entropy rate is computed by the equation 7, and that usually will give me about an equation which is 8, that is a subtraction of a positive definite term called entropy production, this pi here, and a positive or negative term called entropy flow. Entropy flow is what is exchanged from the system to the environment, and entropy production is what the system produces itself. Okay. So this, just to take this into account, because we will use this later in the next slides. Okay. The good thing about all the previous ideas is that maybe I could figure out a way to find some analytical results for specific cases. And a case that I can generalize, at least, is when we have Gaussian dynamics. And that can be achieved if the potential has the following form. So in that case, the solution of the Fokker-Planck equation, doesn't matter the order, given that also the initial condition is Gaussian, it will remain Gaussian at every instant of time. So you will have something like equation 9. And also another good thing is that if I know that that's going to be the shape of the probability distribution over time, thanks to the linearity of the process of the Langevin equation, I can find a set of deterministic differential equations for the mean and the covariance of the process, just given by equations 10 and 11. So you see, when we have something which is linear, we can, even though it's a probabilistic process, we can at least have some sort of deterministic dynamics, but in terms of the mean and covariance. And from there, we can do stochastic simulations. Okay, so what I then, after doing this analysis, and figured out that this could be something useful for in many cases, in many applications that I will discuss later. I think the first will be to try to describe if we could get, for this sort of systems, also generalize the concepts of entropy production, entropy rate, and also see if there is a possibility to apply a technique from information theory that's the main subject of the talk, which is information length. So we can, as we can see from this result and the following, we can compute entropy production and entropy flow from any Gaussian distribution using these equations, which is also useful. And we will see later why, and entropy rate. Okay, so there is this. You can use these formulas that I hopefully I will submit about them and the proof of them in this year, but this is something that we will be using later. Okay, so there is a way to compute entropy production and study thermodynamic quantities from any distribution or any stochastic process, but specifically when talking about Gaussian process, well, there is this that you can do. Okay. If there is some questions, you can just stop me if needed. All right. So
the question. This entropy production, that's the same thing as the entropy production rate, right? Or is it something different?
I think it's the same thing. I think some people, I have seen that as well in some papers. So entropy rate will be the subtraction of these two terms. And
so entropy flow, that's entropy that's created by the dynamic and put into the heat bath. Is that
exactly?
Look at it. Okay.
So this is the one that produces the system, and this is the one that the system exchanges with the surroundings. Also, it is important to mention that entropy production is related to irreversibility. If entropy production is zero, the system is reversible. And when a system is reversible, it's supposed to have the characteristics so that you can extract the maximum amount of work, or possible amount of work. So that's interesting, I think. Right. So this is just something that I would like to remark about entropy production. Okay. So, and also another thing that is important when you study stochastic processes is that, well, you have these probability distributions, and you can connect in that way stochastic processes and this theory with information theory. So let's discuss about the following problem. Imagine you have again this sort of flow of the probability distribution of any given system, and you have the problem of figuring out how this probability distribution is changing over time. For example, it could be maybe to try to figure out a way to find its velocity, or possibly the distance between these two probability distributions. So information length is the metric that does that for you. When computing information length, which is given this formula here, you can find the length of the path that the probability distribution takes over time, given an initial condition and a final condition, the initial time and the final time. This information length, you can compute it by computing the integral of velocity in terms of statistics. Okay, this square root of curly e is a velocity. It has the units of velocity. Okay, but it's dimensionless. At the end, there is no need to know if it is meters or watts, or that's what I mean with dimensionless. So if you see carefully to this expression of what is curly e, is basically information, Fisher information, when you consider t as the parameter of control. Okay, so this is what you get, this integral over the space x. Okay, and computing L, as I have said before, it gives you the total amount of statistical changes that such probability distribution from T0 to F takes. Okay, but also maybe you, since the square root of E is a velocity or rate of change of the probability distribution, you can see the amount of fluctuations that it has taken over time, how it evolves. So you can compute that information length from a stochastic simulation, as the ones that I said before. So this is an example where I do an estimation and theoretical computation of the probability of the information length and information energy. This is usually called information energy. Once you get the square root, people call it information rate. Okay, because dimensions of velocity. So in this case, I'm computing the information energy or an information length from a simple first order stochastic equation. But look, I have to compute like 1 to the times 10 to the 5 solutions of such a stochastic differential equation. So it becomes something kind of busy to do, right? Maybe figuring out a way to compute such value from a formula will be useful, which is something that I got in this article that you can check if you want. So the value of such curly E, or information energy, given that you have a Gaussian process, can be obtained from this formula, which is quite simple. And the good thing is that you can use the dynamics of the equations of motion of the mean and the covariance that I mentioned before. You just substitute them here. You use your mathematical model, of the Langevin equations. And if it is Gaussian, you can use equation 16. Okay. And also, which is another result that I hope will be submitted this year, you can find that such value, which is an entropy theory related quantity, can be related to the entropy production of entropy rate by this inequality. And this inequality becomes an equality when the system is just a first order Gaussian process, okay? And well, it doesn't matter the number of the order of the Gaussian process you have or the Markov chain. Meanwhile, you figured out a way to reproduce it or express it as a Gaussian process. You can compute these quantities and relate entropy production with the information rate or information length. Okay, so this is where just some simulations. I was increasing the order of the linear process and comparing to see if this inequality holds. All right. So, well, if you have a system which is fully decoupled, this is the case where actually a case where such inequality becomes an equality. Okay. But it's again a relationship between a quantity that measures fluctuations and length, or the total amount of statistical changes that the probability distribution took from an initial to a final state, which is something that, as we will see, may be useful. Okay, so you can relate them for some systems. For example, in this case, it is an example of an optical trapped particle in the three-dimensional space. And well, you can compute the thermodynamic quantities and relate them also with the information theory quantities to see what's happening. The idea is, of course, to figure out a way to optimize these quantities. And this is what I will talk in the next slides. Okay, I don't know if there is any question to now, but this is it so far. All right, so the following will be that problem about optimization. What if I want to find the geodesic of the information length? The information length, as I told you, is the total amount of statistical changes that the probability distribution takes over time, and it gives you a length thanks to the application of differential geometry to